Swayam Prabha. Digital India. Educated India.
Good morning, and we will start the lecture on high temperature properties of high entropy alloys today. And when we talk about high temperature properties, and then the first thing which comes to our mind is about creep. And yesterday also I briefly mentioned about this creep properties and then hot hardness properties of high entropy alloys. And then today what I am going to do is give a brief, very briefly we will discuss about what are the creep mechanisms, and then what do we expect based on that mechanisms in high entropy alloy, deformation, high temperature deformation especially. So when we talk about the creep mechanisms, we have four primary types, like one is a diffusion creep, another is dislocation creep or dislocation glide, and then grain boundary sliding. So these are all the four primary creep mechanisms we talk about. And suppose if you assume that these creep mechanisms operate in high entropy alloys, even the superposition of these three mechanisms together in this materials will have a significant effect on the creep rate. So what we will first look at is that we will look at these high entropy alloys as a potential candidate which can have an improved creep resistance. In that perspective we will look at it. But then when you say that improved creep resistance, what are all the additional factors or important factors the high entropy alloys is going to have an advantage as per the literature. Okay. So we are going to have a discussion on this sluggish diffusion factor, whether it is as I mentioned before, this is some research is proving to be not true, but some researchers have told that this is happening. But irrespective of that, let us assume that till date the majority of the literature says that sluggish diffusion exists in these materials, right? So let us first look at the sluggish diffusion factor, how it is going to improve the creep resistance, and then we look at the stacking fault energy factor, which I also mentioned yesterday. Most of the FCC high entropy alloys have very low stacking fault energy. And then the important aspect of atomic size difference factor, which also we will discuss how it is going to improve the creep resistance, and finally the precipitation factor, right? So how all these factors going to improve the fatigue resistance. So let us spend some time on this sluggish diffusion factor. Suppose if you take the diffusion and dislocation creep model or mechanisms, steady state creep rate is directly related to the diffusion rate in the alloy. So whatever diffusion or dislocation creep, the diffusion rate is the primary parameter which you have to look at. And of course the activation energy for the creep is essentially equal to that for the diffusion. Especially when you look at the diffusion creep, then the activation energy, whatever you derive for this activity, then that can be directly correlated to the creep. Sluggish diffusion in high entropy alloys has benefit to have a better resistance to creep. How? How are we going to qualify this statement? Because if you look at the grain boundary sliding is also inhibited because diffusion in the vicinity of the grain boundaries to support the diffusion and dislocation creep is sluggish. So this leads to an enhanced resistance to creep. Okay. When you say the diffusion is the most rate controlling step, then the sluggish diffusion is supposed to improve the resistance of the creep. Okay. And of course, in the components, when we are talking about multi-principal component alloy, one component having the slowest diffusion rate could become the rate determining step in in most of the high entropy alloy systems. So this demonstrates the benefit from high entropy alloy composition, which contains appreciable amount of major elements. If the slowest component is added, its power to determine the creep rate would be significant. For example, if you take a refractory BCC type high entropy alloys, which have a common melting point over 2000 degrees centigrade, okay, all these sluggish diffusion effects might compensate the higher diffusion rate in the open pack structure of BCC matrix. This is also another contradicting factor which we have to look at it. Okay. But the literature currently reports that the sluggish diffusion factor plays a significant role in improving the creep precision. That is the knowledge as of today. So let us look at the stacking fault energy factor. Solute addition has been found to lower the stacking fault energy, such as what we have seen in a common alloys like copper aluminum or copper zinc, due to the interaction between the solutes and stacking fault. And yesterday I also talking about the Suzuki effect, right? The segregation along the stacking fault also is a Suzuki effect, something like that. So it is well known that the low stacking fault energy of a pure metals solid solution strengthened alloys have low creep rate. So this is already known fact in the literature. Okay. This trend can be explained because low stacking fault energy causes a dislocation difficult to overcome the obstacles by cross slip. This again we discussed yesterday. So this makes dislocation mainly use claim process to overcome the obstacles, although the actual model or mechanism is still not very clear. Okay. This trend suggests that low stacking fault energy has an advantage in reducing the creep rate. So wherever you have a obstacle for the diffusion or any dislocation migration, especially in a three-dimensional motion, that is also supposed to reduce the creep rate. So if you look at the FCC high entropy alloys have a quite low stacking fault energy, they have a potential to have a better creep resistance. So this is another factor which is going to significantly contribute to the creep resistance. Coming to this atomic size difference factor, if you take the polycrystalline nickel, solid solution strengthening has been found to increase the time to fracture under the same stress, because this is a general knowledge from the solid solution strengthening. And in addition to that, if you have a large atomic size difference gives a large creep resistance, that means higher stress at the same stage 2 strain rate. When you say stage 2 strain rate, it is a steady state, right? Steady state creep rate. So even a larger atomic size difference could reduce the stress component from 5 to 3 as mentioned above. And then furthermore, higher content of solutes gives smaller creep rate. So the more mixing promotes the smaller creep rate. Okay. So above this trend, it appears that multi-principal element solid solution phases in high entropy alloys would be beneficial to the creep resistance because they essentially possess the whole solute matrix and have solute dislocation interaction everywhere. Okay. So this is very important point. So you have all the whole solute matrix have a solute dislocation interaction all the point, because it's already a strained lattice. So let us look at what we already know. In nickel-based superalloys, gamma prime phase not only enhances the high temperature strength, but also increases the creep resistance. And of course, the variable is the gamma prime phase fraction. Higher volume fraction could increase the creep resistance. For example, if you take this mnemonic series, about 80A, 90, 105, 115 alloys, they have the gamma prime fraction of 0.17, 0.18, 0.32 and 0.62 respectively, also to have improved creep resistance. The temperature of the mnemonic 115 alloy, okay, for 1000-hour creep life is 137 MPa, is higher than the first by about 120 degree. That means mnemonic 115 alloy have a better creep resistance than the mnemonic 80A. So that is the idea. In addition, we talk about lattice misfit between gamma prime phase and gamma matrix. and also solvus temperature of gamma phase are all important for factors for creep resistance. Small lattice fit means less coarsening rate of gamma precipitates, and high solvus temperature means higher thermal stability of gamma prime phase at higher working temperatures. These ideas are all well known, but why are we discussing this? Suppose if you bring all these ideas into high entropy alloy design, okay, then what happens? So that is the idea. As a different solute elements have a different partition between gamma prime phase and a gamma matrix affecting the lattice misfit, shear modulus, coherency and stability. Then how to design high entropy superalloys based on the conventional superalloys is a good research topic to obtain improved properties. So this is all some of the guidelines we have already got from the existing conventional alloys. So it can be used to design high entropy superalloys for improved creep resistance. So these are all the another important points to observe. The last one is the precipitation factor, and small addition of boron and carbon for forming boride and carbide particles could increase the resistance of grain boundary sliding. So grain boundary sliding is one of the primary creep mechanisms. So if the precipitations are there on the grain boundary, it will stop the sliding. That means it resists the creep. Okay. For example, Key and Knowles tested an experimental second generation superalloy in a creep at 950 degrees centigrade and 290 MPa. Addition of 0.09 weight% of carbon and 0.01 weight% of boron could improve the rupture life from 10 hours to 100 hours. Okay. So either you look at the creep strain or the rupture life. These are the two types of tests that high temperature people do, right? So this is because the small carbide M23C6 type formed along the grain boundaries. So the improvement is significant. It's about 10 times the without the small addition of carbon. So this method also can be used for improving the creep resistance for polycrystalline high entropy alloys. Okay. So we have some idea keeping all these factors, sluggish diffusion, atomic size difference, stacking fault energy, precipitation factors, all these are going to affect the creep resistance of high entropy alloys. If you look at the literature, the experimental data available on these high entropy alloy on creep data is almost nil till 2015. Okay. Very small experimental data is reported, and this is one among them what I am showing. He et al. Reported the steady state flow behavior of cobalt, chromium, iron, manganese, nickel high entropy alloy in the strain rate jump tension tests at temperature ranging from 1023 to 1123 K. They used the power law to fit flow behavior with the stress and temperature shown here. So what you see here is the steady state strain rate, that's a creep rate versus stress, and then you have a creep rate versus homologous or temperature, inverse of temperature, not homologous, it's inverse of temperature plot. What you see here is a distinct two regions, region 1 and region 2, and we have a test conducted at different temperatures, what is shown here. Okay. Region 1 with a low stress exponent at a low strain rates or stresses, and the region 2 with the high stress exponent at high strain rates. So what is this stress exponent? Why do we try to get this stress exponent? Any idea?
Which mechanism it is for?
Okay. Usually stress exponent is related to a particular mechanisms associated. If you are able to do it like if you do the creep test at different strain rates, then this is possible to get, you can get the stress exponent. So it is nicely shown here, like you have a different type of, two different stress exponent values you get, and then you can also calculate the corresponding activation energy for this. So what you are seeing here is a steady state strain rate as a function of true stress on a double logarithmic plot, shows apparently two deformation regions marked as 1 and 2, and the steady state strain rate versus inverse of temperature on an Arrhenius plot showing an apparent activation energy of 280 kilojoule per mole for region 1 and 330 kilojoule per mole for region 2 respectively. The important point note here is the activation energies for this lattice diffusion in this iron, cobalt, nickel, chromium, manganese alloy are comparable. For example, it is for the nickel, it is 317.5 kilojoule per mole, chromium it is 292.9 kilojoule per mole, and for manganese it is 288.4 kilojoule per mole. So you can see that these values are very close to what is being calculated for this particular alloy. So that means you can say that it is lattice diffusion is the primary mechanisms in this. So the stress exponent of about 5 in region 2 suggests that the dominant deformation process is dislocation climb. The activation energy is around 330 kilojoule per mole, can be rationalized by the slowest diffusing species of nickel, which controls the rate process. So this is what I showed. You have this lattice diffusion of nickel is about 317.5 kilojoule per mole, and you get this value activation energy 330. So you can relate that with nickel diffusion, and the mechanism is basically dislocation climb. Okay. On the other hand, the stress exponent of about 3 in the region 1 suggests that the mechanism is drag of gliding dislocation drag. So however, the lower activation energy of 284 kilojoule per mole is difficult to rationalize by the slowest nickel, but when region 1 in figure is rechecked, an activation energy of the same as region 1 might be expected. This again confirms the rate controlling is still the slowest nickel. Okay. So the dislocation are supposed to migrate. So if your second phase particle will try to drag them, so then your dislocation creep will be resisted. Okay. So that is why it is. And the another important point I want to mention about this high entropy alloys is the structural stability, right? How much stable these microstructures are. If you recall yesterday's lecture, we discussed about hot hardness and then indentation creep and so on. They are all related here, because we discussed the indentation at very high temperature and how resistant they are, or how resistance to softening basically. They are all related here to the high temperature properties. So if you look at this diagram, what we have shown is again a hot hardness of different high entropy alloy compared with some of the conventional alloys like SKH51, SUJ2, Inconel 718 and so on. So what do you see? What is the description? Can you, based on the yesterday's discussion, can you describe this? So you have evidence that many high entropy alloys have an exceptional high temperature strength hardness, which originates from their excellent resistance to thermal softening. Okay, this is the bottom line. They are quite resistant to thermal softening. How do we know? You can see that the conventional alloys like SKH51 or SuJ2, what do they have? How do they react? There is a sudden drop. The moment the temperature increases, you can see the drastic drop in the hardness. And if you look at all the high entropy alloys, the change is quite gradual, right? So that means the thermal softening is highly restricted here. Okay. So all these high entropy alloys have very high hardness at room temperature, more than the 2 times higher than Inconel 718 superalloys, and their hardness decreases slowly with increase of temperature, but the conventional alloys have a very high hardness at room temperature, but they drastically changes with the increasing the temperature. This is another important point. So what is the advantage? This leads to a significant difference in the hardness for the 4 alloys at 800 degrees centigrade. The 2 high entropy alloys still more than 2 times harder than the Inconel 718 superalloy, while the 2 conventional alloys become apparently softer than Inconel 718. So at 1000 degree, the high entropy alloy is already more than 3 times harder than Inconel 718. Also, you can note that even the soft sole FCC high entropy alloy is quite resistant to thermal softening. So these are all some of the interesting results comparing the conventional alloy, where it shows the superiority of high entropy alloys having the higher resistance to thermal softening. So what we are going to see is again some experiments conducted by Su et al. Calculated the high temperature softening coefficient for the aluminum, cobalt, chromium, iron, moly, nickel alloy with varying iron content from 0 to 2. From the hot hardness versus temperature curve, he has derived a high temperature softening coefficient and found that above the transition temperature, that means the onset of temperature for rapid softening. For example, when I look back this curve, so I would say that the transition point somewhere at 600 degrees C for SKH51, but for SuJ2 there is no sharp transition point because it is continuously rapidly decreasing. So when you say the transition point, I mean this. There is a gradual transition, then abrupt transition. So that is what is mentioned here. So the onset of transition temperature, transition temperature for rapid softening, the softening coefficient for these alloys are evidently low than that of the conventional high temperature alloys such as Inconel 718 and T800, what is shown here. So you can see that the conventional alloy have the softening coefficient much higher than the high entropy alloys. So you can see that the softening coefficient of some of the alloys are even less than half that of conventional alloy like Inconel 718. The resistance to thermal softening is mainly as a result of sluggish diffusion in high entropy alloys. That is the belief as of now. So above this transition, what happens? So the deformation proceeds via diffusion related mechanisms, and that slower diffusion rate in high entropy alloys can effectively reduce degree of thermal softening. So thermal softening is an important parameter to characterize the high temperature stability or structural stability of the high temperature alloys. Suppose now we can look at the same thing, instead of hot hardness, we look at the yield stress versus temperature plot. Because the transition temperature and diffusion rate of metallic materials are directly related to the melting point of the material, it can be expected that refractory high entropy alloys should have outstanding properties in this regard. Because all the refractory elements have high melting point, so you make a high entropy alloy out of this, which is expected to have a superior, I would say, resistance to thermal softening. For example, you have a tungsten containing refractory alloys have an excellent resistance to thermal softening. This is shown in the figure. So, what you are seeing here is you have niobium, molybdenum, tantalum, tungsten, they are all equal proportion, and then you have vanadium, niobium, molybdenum, tantalum, tungsten alloy. You can see that the yield strength is very small change with the increasing temperature. On the other hand, you see this Inconel has got a drastic transition beyond 600, and Haynes also softens much rapidly as compared to these two high entropy alloys. So, these results clearly demonstrate the structural stability, and what you are witnessing here is the yield strength of these alloys remain virtually unchanged in the temperature range, especially between 600 to 1000 degrees centigrade. So, this plateau we are talking about, though they have extremely high yield strength over 400 MPa at 1600. So, even at 1600 you have the difference of about 400 MPa compared to this conventional alloy which softens significantly. Owing to their good strength at high temperature, some refractory alloys actually have higher specific yield strength than the superalloys, such as Inconel 718 and Haynes 230 at higher than 1000 degrees centigrade. So, you have make some general statements here. High entropy alloys generally have a good structural stability at high temperatures. This is primarily due to slow kinetics, due to the sluggish diffusion effect. Second is the reduced driving force to eliminate defects, that is grain boundaries, interfaces, etc. There is much evidence for the good structural stability in high entropy alloys. For example, the activation energy of grain growth for this cobalt, chromium, iron, manganese, nickel alloy, which has a sole FCC structure, is about 321.7 kilojoule per mole. This value is twice that of 304 Ln stainless steel, indicating significantly slower kinetics for microstructural coarsening, and growth of precipitate in high entropy alloys is also pretty slow. And what people have again tested is precipitate in the high entropy alloys treated at moderate temperatures at 700 to 800 degree. They remain in small diameters on the scale of tens or hundreds of nanometers. Okay. They are also not reporting any significant growth of this precipitates. Another example is for the structural stability case study is that you have the high entropy alloy of niobium, silicon, tantalum, titanium, zirconium, amorphous alloy. Okay. The crystallization temperature of this alloy is higher than 800 degrees centigrade. This temperature of stability is probably the highest among reported amorphous metals. This is quite interesting, right? So, the excellent structural stability comes not just from the above two reasons, that is what I just mentioned here, the slower kinetics of sluggish diffusion or reduced driving force to eliminate. These are the two effects we are talking about. And this alloy was designed based on the free energy consideration. Okay. Its composition was selected so that the non-crystalline random solid solution state has low free energy. This lowers the driving force to crystallize to silicides, and additionally the kinetics in this alloy is further slowed due to high atomic packing density and high melting points of composing elements. Okay. So, when I talk about these high temperature properties, as I mentioned, we have very limited experimental data available in the literature, and most of the some of the reports showed in the literature is these alloys are being used as coating, high temperature coating mostly, and but they are also not widely reported in most of the literature. Okay.